So have you read like Silmarillion and all those?
Oh yeah, yeah. Okay, so all right, so let's go through an optimization problem here then. So something like this, we got to go through our steps, right? So you have that little handout, but you probably don't need it. What's the first step in an optimization problem?
Get your variables.
Okay, good. So we need to represent it, probably visually, done, right? And then we need to assign variables. Okay, so we're maybe not quite done though, because what we're trying to maximize here, I want you to think about this. We want to find the volume of the largest right circular cone that can be inscribed in a sphere of radius r. So tell me, please, oops, wrong one, hang on. While I'm taking roll, I want you to think about this. Is r a variable? No? That's correct. It's not a variable. It's a parameter. Because it wouldn't make sense for r to be a variable. If r were a variable, what's the obvious answer? It's the cone is going to be infinity by infinity, right? Wouldn't make any sense. So we are going to constrain our variable cone to be inside a fixed radius sphere. We didn't give it a number, we just called it r though, but r is considered to be a constant. Okay? So this is a pretty fancy picture, but I think we can do better. I think it's overly complicated. We should probably, how could we simplify the picture we're going to work with? Does it need to be 3D? No, it doesn't really, does it? Why don't we take a cross section through the middle, right? Does that make sense? So if we make a cross section through the middle, this is going to be a little easier to deal with. So there's the cross section of the sphere, right? And now, what's the cone going to look like? Just the generic cone. Yeah, it's just going to look like a triangle, isn't it? It's going to look like there's going to be the base. And how's that right there? That's pretty good, huh? Something like that.
Okay. You should use a triangle shape, will you?
Yeah, triangle, it doesn't work as well because the whole thing distorts. You can't really control where the vertices go. So there's our cross section, right? So what is the formula for the volume of a right circular cone?
4/3 pi over,
It's going to be, now here's a way you can think about this. It's going to be a fraction of the volume of a right circular cylinder, right? Because if you started with a right circular cylinder and you were to carve out the cone, the biggest cone would have the same height, right? But the apex of the cone would be in the very center of the circle that forms the top of the cylinder, and you just shave it down to where the bases are the same. Does that make sense? What's the ratio? What fraction of that?
So that poses the question, what's the?
It's 1/3. Yeah, it's 1/3 of the volume. And so really all it is 1/3 times pi r squared h, right? Pi r squared h is going to be the volume of the cylinder, and it's just 1/3 that much. Okay. So then we're going to need, our variables are going to have to be, we're going to have the radius of the cone. What do we call it? X. Okay, so this distance right here. So that distance right there is x, which would correspond to that distance right there. Right? And then what else? We need height of the cone, right?
Yeah.
Height of the cone would be up here. This is going to be the height, which we'll call, how about y? And right here, that's our y. Okay? No big deal, right? And so what's our formula going to be then for volume? Well, pi x squared y. Okay, what's the problem with that?
Two unknowns.
Two unknowns. Yeah, so we got to find a way to relate those, right? So we need a secondary equation, sometimes called an equation of constraint. That's the key word.
Yeah.
And that's important because the secondary equation is always going to be from the constraint. Which if there's a number involved, would be the number. We don't have a number, but what's our constraint?
The radius.
The radius. Yeah, so it must involve the radius, right? They didn't give us the radius for nothing. That's gonna be what relates to variables. So how am I gonna come up with a relationship between x and y and r? R is the radius, correct?
Oh, that's in there.
Okay, yeah, because look, if I draw the radius in a couple of tricky ways, the radius is gonna be that distance from there to the edge, right? Okay, but let's pick some smarter versions of that. This is gonna be r, right? And this is gonna be r. Okay? Make sense? So I have a right triangle there, right? Right triangles are gold. That's great because I can relate the sides of a right triangle by the Pythagorean theorem, right? So if I take my right triangle here and let's just drag that out. So there's my right triangle. What are the sides? X is the base,
And y minus r,
R is the hypotenuse.
and then there's
Y
y
minus R.
Very good. And this distance right here is just gonna be y minus r, right? Okay. That's all I need. I've got all three of my quantities represented in the three sides of that triangle, so we can come up with a pretty easy equation of constraint. What's it gonna be?
r squared
X squared plus,
y minus r squared.
okay?
We decided it was too much for the
Yeah. But then he was just chilling outside the door.
Oh, was it?
Yeah.
Okay.
And then he like looked in and he's like, nope. He just left.
Okay, so what do we got? What we can do with that maybe?
Through them.
No.
You
Just
wanna
throw it outside.
That's
decide
a
which one
good
you
general
wanna-
answer in calculus, isn't it?
Or what kind of, you wanna figure out which one you wanna substitute.
But, okay, you're right, we wanna figure out which one we're gonna substitute. But in order to substitute, I probably gotta clean this thing up a little bit, right?
Yeah.
Okay, so what could we do here then? I can expand that out, right? So then if we do that, we're gonna end up with x squared plus, what is the expanded version of that?
Y squared.
Squared
Minus two y r plus r squared.
Okay, that helps. What can we do?
Can you get rid of r
We
squared?
can get rid of the r squareds. Okay, now clearly, which variable are we gonna substitute for? It's not even close.
X.
X squared, how about,
X.
right? You see that? Because look, I've got an x squared there and I've got an x squared there, and each term only appears once in each, right? It's a single factor here, it's a single term there, right?
And there's the same thing.
Exactly, so look what we can do then. We can write this down here, we can solve this for x squared, and I'm just gonna get positive 2yr, oops, 2yr, what did I do? I was thinking
y r.
2yr minus y squared, agree? Okay, so put a box around it. There's my substitution equation, and now I can take my original and my substitution equation, and I can build my primary equation, which is what we call this, right? We always start with that, the quantity we're trying to optimize, in this case maximize. We're gonna write that as a function of one variable, which is gonna be what?
Pi 2yr minus y squared.
Times y, right?
Yeah.
Okay, so then that's just gonna be pi times the quantity, 2 y squared r, everybody agree? Minus y cubed.
What'd you do?
I just that's my x squared, so I just plugged that in up there and distributed the y.
Why not do the r again? Why not distribute the square to the r?
No,
The-
there's no square, it's just the y. He's multiplying the y.
See, all I'm doing is I'm taking this expression right there and I'm plugging it in
Yeah.
right there.
Anyway.
Okay, make sense? Okay, so that's what I get, so then I can write this as v of y.
Ooh, there's
Because
the
y is my
derivative.
independent variable.
There's the derivative.
Mm-hmm. Aha. And now we're ready to just do calculus, right? So we've got our primary equation, right, as a function of one variable. So now I can just do calculus. There's one other piece we need though. We need the domain. Okay. So we got to think about this. Now mathematically, there's no restriction as to what y could be, right? But physically there is. What's the smallest that y could be? Now think about this in terms of here. This is kind of fun. Let's build some. How much time we got? We have time to have some fun here. Oh yeah, we have time. Okay. So, this is so fun. We get to do such fun stuff in here. Oh my gosh. So let me pull up Geometer Sketchpad. Where is it? Oh, there it is. Yeah, we're getting real fancy here. So let's visualize this because there's some value to that. You know, you're not going to do this every time, obviously, but we'll do it this time. Okay, so I'm just going to make a circle. Let's redo that. About right there. So there's our circle, right? And I'll even, how about if we just like move this circle so it,
Ooh, that's cool.
I meant to do that. I'm kind of out of practice with my Geometer Sketchbook, but it's really fun. So then let's draw, how am I going to get a point at the exact top of this circle? I used to make, see, I didn't have you guys, but I made, we've done, like in my honors geometry class, I made them do a bunch of Geometer Sketchpad constructions. We even did it in honors algebra 2 a little bit.
Isn't it something like drawing numbers? No, not drawing.
I'm gonna, you know what? I'm gonna make you guys do this a little bit. I'm gonna give you, these are fun assignments. I'm gonna make you do some calculus with Geometer Sketchpad at some point, okay? And there'll be some times when it'll really make sense to do. So all I have to do is this. I can grab this point right here, and I can just say I'm gonna construct, oh, actually, hang on. I have to grab that point, and then I have to, how do I do that? I go,
Why don't you just put the other point?
well, but I want it to be at the very top of this thing. So
Don't you have to make a point at the top and then you can like make a line and then make it like in the middle?
I think I have to make a number so I could construct a point.
I haven't done this since I completed.
Oh, here's what I can do. Okay, let's do this. I'm going to do, well, I'm not going to, you know, if this ends up being too much time, I'm not going to do it. But I think I can type in a value. I think I can do like, I think I can do slope. Let's try this. So if I go,
Why not just draw like another circle off that point and then like make the middle like, you know what I mean? Like, and then the center point of the other circle, you put a line through the two, and that would put a line right through the top of that circle. That would be
yeah, the only thing I just wanted to do, I just wanted to make this line vertical. And I know there's a super easy way to do that, but I'm just not seeing what it is. So I guess I could do, I think if I hold down shift, maybe that does it. If I do line, and I go, yeah, there we go. If I shift, okay, I create a vertical segment. Okay, oops, I always do that every time I do that. There we go. Okay, now we go here, and I'm just gonna create a point at that intersection, right there. Okay, and so there's one point. Now I'm gonna create another point right down here, which I already have. Oh, hang on. I don't want to use that point. I'm gonna make that one disappear. Actually, I'll screw things up if I don't make him disappear. So hide point. Okay, now I'm just going to create another point that's on this circle, right? And so that's a point that I can drag around. It's just constrained to be on the circle, okay? So I want to then, I'm just going to create a horizontal line through that point. Okay, and then obviously you can see what I do now. Right now I'll just put another point at that intersection. And now all I've got to do is just construct, connect the dots, exactly. There we go, okay? And so I believe at this point I can do everything I need to do. I think I can grab this guy. Oh, no, I can't.
There you go. Save that. Oh, geez. I'm done. That's
Darn it. Okay, here we go. Okay, so now I can do this. I can create a segment.
Yeah, just like that. Create distress. Creating distress and loving stress.
There we go.
Distress.
Oh, I know what I can do. I know what I can do.
Stress.
Okay, there's another way I can do this.
Of course it is.
So I can define, oh, not like that. There we go. Okay, there we go. So I'm going to define this as my mirror. And I'm going to do that stuff, and I'm going to reflect. Okay. Fancy, huh? And then I'm going to connect these points. So you guys, can you kind of see how this is kind of fun? I mean, you get to do some pretty cool stuff. So now I should be able to drag. There we go. Okay, so there's my cross section.
Okay.
You thought I was going to not be able to pull that off. I know. Braden, you had no faith.
But I figured you'd eventually get it.
I just thought it would take so much longer.
Yeah.
Wait,
So there it is, right? Okay, so we could actually do a volume calculation in Geometry Sketchpad, but I just want you to think about what would be the smallest logical choice for H. I mean, would it be 0? No, it wouldn't be, would it? Because we could logically say, all right, I mean, without affecting the calculus, what would be the minimum value for H that we would ever consider? Yeah, the radius, right? And here's why, because if I were to, for example, choose that value, well, would you agree that that has the radius of the cone there is going to be the same as it would be, right? There. Everybody agree?
Say that again.
So those two cones have the same radius, don't they? Right? You agree? The top one and the bottom one? Let me get rid of, oops, gosh. Let's get rid of him and him. Right? So I get the short cone and the tall cone both have the same radius. Which one obviously has more volume? The bottom one. So why would we ever do anything other than just start at the middle? See what I'm saying? And then I could drag it down further and create. Okay? Agreed? All right. That's a lot of work to show you. But I also kind of wanted to show you. That's fun. You guys would like that. You guys would really like that. I got to get
So
you
doesn't
going.
that mean that like the largest volume of the cone, doesn't that, it's the sphere then that like dictates that?
It is. Right. The sphere dictates that. So, but when we're coming up with our domain, with the working domain for our specific problem, we could say it does have a lower limit. The lower limit for y is going to be R, right? What's the upper limit gonna be?
Upper limit's gonna be
Well, let's go back to
2R.
another, I can play some more. Yeah, it's 2R, isn't it? Because look, I could drag this thing down. I could keep dragging it down. It's going to get taller but skinnier as I do it. And right at that point right there, I don't know what happened there, but it goes away, right? See what I'm saying? Okay? Okay, so
It's like the height.
so there it is. So now we are firmly into calculator mode. So or calculus mode. We just flip a switch now and we forget about the geometry problem and just do calculus. And when we're all done with calculus, we'll come back and interpret it in terms of the geometry. But really, all we got going now is just that function. There's our domain. That's a polynomial. That's an easy one, right? What's v prime? Of y, sorry.
You have 4,
I can leave the pi out front, right?
you have 4y,
Okay.
r, no. Get rid of the r.
Or no, the r is not a variable,
Oh,
remember?
constant.
It's a constant.
So would it stay the
Minus
same?
3y squared.
Yeah. Right?
So constants stay the same?
Yeah, what's the derivative of a constant? 0, right? You know how to deal with constants. When we have a constant multiplier and we take a derivative, the constant just stays out front. So technically, we might want to put that r out in front, but we don't need to, right? The only variable here was the y squared. I had 2r times y squared, so multiply the 2 out front, and I get a 4r times y to the 1, right? Okay, and then while we're at it, what is v double prime of y?
Wait, what do we use the double prime?
Because
You just
it's
need
easy to
geometry.
do, and so we can use the second derivative test. We always would prefer to use the second derivative test over the first derivative test. Remember, we work as far down the table as we can. So v double prime is going to be what then? Pi times 4r minus, okay. So this is simple. We'll find the zeros of our first derivative. Well, what are those going to be? We're going to end up with v prime equals 0 when, if I factor that, I can just pull a y out, right? I can write this part as pi times, yeah, pi y times 4r minus 3y. So where are the zeros?
0.
When y equals 0 or,
Let's see. 3/4.
mm,
3/4 R.
Or r equals 3/4 pi.
if I set that equal to 0, what am I going to get?
R equals 3/4 y.
But I'm not solving for r.
Okay, so y, oh.
Right, y is the variable, so y equals
4/3.
4/3 r, okay. Okay, 0's no good, that's not in our domain, but 4/3 r is, right? Okay, so logically, we could just reason that has to be the solution, doesn't it? Right. We know there's gonna have to be a maximum, so that's it, but we could show it pretty easily on our table. Right, if we make our table, let's, man, I always run out of room. Let me just do this, so if I grab,
Please. It's worth more than the car.
okay, so there's a summary of all our stuff, right? So we can make our table.
Do you need to where the second derivative is 0?
No, we don't, because all we're trying to do is optimize, right? So then, so you see what I'm saying with the optimization stuff, the word problems, the calculus gets easier. There's less to do, right? But all that stuff you did in 3.6 pays dividends now. So our domain was R to 2R. We had one critical number, which was at 4/3 R. That's where the first derivative was 0. Well, what's the sign of the second derivative gonna be? If I evaluate this at 4/3 R, I'm gonna get 4R minus 24/3 R. Right? So that's gonna give me an overall sign of what?
Negative.
Negative, yeah. So then what is this? It's a horizontal tangent, concave down, AKA maximum. Okay, and so, what did they ask us to do? I guess I forgot what the original question was even. Does it want dimensions, or was it want the volume? So where would I go on my chart to, to find volume?
V.
Yeah, V. So I'm just gonna evaluate my original function at 4/3 R, right? And you can, yeah, that's no big deal. If I plug 4/3 R up in here for Y, I'll just get some answer in terms of pi's and r's and fractions, right?
That would actually like time right. So.
How about that? First time for everything. Right?
Now on the
Elfish.
That's pretty cool though, huh? And that's a hard one, right? So you get an idea, I mean, that's,
That wasn't a hard one. I feel like that is, the hard one.
well, it's calculus. They're supposed to be hard.